Awesome. Thanks for the great talk, Sabine. Our next talk will be from Phaedra Upton, who's a principal scientist at Science in geodynamics and tectonic geomorphology. And she will be presenting on the tectonic evolution of the Marlborough Fault System. So I think we'll pass that. I'll pass that on to you, Phaedra, and you can start to share your screen. Cool. Looks good.
Good. I'll just turn this into a... Okay. Tēnā koutou katoa. It's great. Thanks. I just want to start by thanking the organisers of the Landscape Live series. It's a really privilege to be invited to speak here, and especially on our time zone. I've watched lots of the other ones, but always after the fact, because 3 a.m. wasn't very appealing. Thanks for a great talk, Sabine, and I think I'm going to take, in a way, a similar approach, but downscale just to a region within Aotearoa, New Zealand. So firstly, though, I need to acknowledge my co-authors. They've all brought their expertise and knowledge of the Marlborough region to this study, and my role has been very much just to integrate all their really good information across the disciplines into what we hope is a coherent story about the evolution of this region. So here's essential Aotearoa or New Zealand from space. It was kind of lurking right on the edge of Sabine's, a lot of his slides. This is the aerial portion of a much larger, largely submerged continent, Te Reo Māori or Zealandla. And it contains tectonically the plate boundary between the Pacific and Australian plates. And you can't do geomorphology within New Zealand, I don't think, without taking into account the tectonics and the tectonic history. So there's the subduction of the Pacific plate beneath the North Island here and the Hikurangi subduction margin. In the western part of the South Island, we have the Alpine Fault and the Southern Alps, which is an oblique collision zone. And linking those two is the Marlborough Fault System, and that's our focus today. It's a complex 4D transition zone. It's really evolved over the last 10 million years, but the tectonic history of the rocks go back much further than that, really back to the Cretaceous. And so what I want to talk about today is how that long tectonic history is visible today and really important when we're thinking about the evolution of this region. So just to quickly introduce the Marlborough Fault System themselves. So here's the South Island, the northern part of the South Island of New Zealand, as I said, between the Hikurangi subduction margin of the north and the Alpine Fault to the south. And the main part of the fault system is made up of these 4 faults: the Wairau Fault, which is the continuation from the Alpine Fault of the boundary between the 2 plates, so Australian plate affinity rocks over here and Pacific plate over here. Then the Awatere Fault, the Clarence Fault, and the Hope Fault. And today, about half of the motion from the Alpine Fault is transferred up onto the Hope Fault, so it has about 20 millimetres a year, and then up through the Kekarengo and out here to join up with the subduction zone. The Marlborough region is mountainous. So here this is the northeast. This is looking along the inland Kaikoura range. In this part of the region, we've got these long linear mountains, inland Kaikoura. So this is the highest mountain in the region, and then bounded by these long linear river valleys, which contain the main fault. So the Clarence Fault on one side and the Awatere Fault on the other. And these ranges were brought up in the early Miocene, so that this range was brought up on the Clarence Fault when it was a thrust fault. The Clarence Fault now, this is the Clarence Valley now looking south, the seaward Kaikouras and the inland Kaikouras, and the Clarence Fault now, which is largely strike slip, and all of these 4 main faults are largely taking up strike slip motion, which it sits right along here. And if we look, and this is what it looks like in the field, a couple of geomorphologists for scale, and that's the trace of the Clarence Fault just running through there. If we move to the southwest in the Marlborough region, we move away from those long linear ranges to more blocky ranges, which are cut by rivers and faults that often intersect in these kind of intermontane basins like this one here along the Awatere. We see the Awatere Fault, several strands of it cutting through the landscape, which is beautiful exposures of these faults. This is the Wairau River here. The Wairau River actually starts on the Awatere Fault. It takes a 90-degree corner and ends up flowing along the Wairau Fault. And this was likely the site of some sort of river capture event, probably due to damming by glaciation during the glaciations. Here, this is a bit further to the south of that last photo. And here, this is the Fowler Fault, which is a subsidiary fault to those main Marlborough faults that's parallel to them. And here, that fault is cutting across a big north-south valley, and we'll talk more about the north-south valleys later. And this fault is quite an immature fault, and it cuts across in this direction. And of course, this region is well known for the 2000. Oh, I've got the date wrong. The 2016 MW 7.8 Kaikoura earthquake that ruptured along the southeastern edge of the Marlborough Faults region. It's interesting for many reasons that we don't have time to go in for, but it started down here in the southwest and propagated up to the northeast. And as it ruptured, it broke lots of small faults which tend to have an easterly or northerly orientation. And then once it got up here, then it got onto the Hikurangi and Needles in a much more just continuous rupture. And there's just a few photos from the field at the time. But today I'm going to talk about the Marlborough region in general and the tectonic geomorphology of that region. And I guess what I'm going to argue is that obviously the boundary conditions, the fact that this region is sitting in that transition zone within a major plate boundary is driving some of what we see. But there are other things that are really important when we think about the evolution of this region, and the lithospheric structure and the tectonic history of the Marlborough region through inherited structures. And these are Cretaceous subduction, which was occurring along the edge of the Gondwana margin, then extension with breakup, then the inception of the Southern Alps oblique collision. And since all these features impact the tectonic geomorphology, we could turn that around, and the tectonics, or the landscape of this region actually contains a wealth of information about these processes and about their interactions, so we can kind of work forward and work backwards. To do this, I'm going to quickly review the current tectonic setting, go through the tectonic history, particularly the Cretaceous subduction breakup, and then the inception of the Pacific Australian plate boundary. Talk about what we see in the landscape by using the tectonic anisotropy and how those inherited structures have played a role. And then I'm going to speculate briefly on what I think that the evolution of the plate boundary, well, how it's going to evolve over, say, the next million years or so. So yes, so here's the Marlborough region here, sitting at this transition zone between subduction of the North Island, of the Pacific plate beneath the North Island, and the oblique collision along the Alpine Fault and forming the Southern Alps in that oblique collision. And it's about, this is the relative plate vector, and you'll see that it's that vector in this area is largely parallel to those valleys and the faults that are in those valleys. So they really are taking up largely strike-slip motion at the moment, despite, as I said, a quite mountainous region that we can just see in this tectonic, in this picture here. Won't let me advance. Okay. So as I say, I argue that Zealandla, the continent that New Zealand's sitting on, it gained a lot of its structure as part of Gondwana and then during separation from that landmass. So if we go back to a large scale picture here, Australia and Antarctica, and sitting along the margin of that was the subduction zone, and the rocks that became Zealandia and New Zealand are sitting right here. And the rocks that became Marlborough that we're really interested in are forming in the accretionary prism. This is the Hikurangi Plateau, which was an oceanic plateau that formed adjacent to the Ongton Java and separated off, and eventually hit this margin at about 100 million years, ended up jamming it up and so partially causing subduction to stop around that area. And that's the Hikurangi Plateau still plays a major role in the deformation of New Zealand to this day. So if we look at that area in a bit more detail, this Australia, East Antarctica, West Antarctica, here's the subduction zone, and the accretionary prism, which is what the rocks of Marlborough are made up of. The arc out here, then the Otago schist is here, and then closer to this younger rocks are what we see, the bedrock of the Marlborough region today. So this is quite a complicated slide, so I'll try to go through it slowly. This is largely based on work one of my co-authors, Andy Tulloch, and his co-authors. And if this is, we go back to the reconstruction here at approximately 90, there's the South Island of New Zealand, again, Australia and Antarctica over here. And Marlborough was sitting right in this region, right near where there was forming, those rocks were forming in the accretionary prism, pretty much about where the Hikurangi Plateau was impinging. And so long-term subduction, which deposited the Paha terrain, so our bedrock, then the Hikurangi Plateau impinges into this margin and subduction ceased. And then followed that there was extension and breakup. And there was two phases of extension and breakup, shown here by the red and the black arrows. So the red is the separation of the Zealandia continent from Australia and East Antarctica, so the Tasman Ross extension. And Andy and his colleagues have looked for the signals of these extensions all over Zealandia, and that's what's shown in this map here. So the red arrows are where they see evidence for structures that were formed as part of this early rupture between Zealandia and Australia, and that was from about 100 to 89 with rupture in 84, and then the second stage was between Pacific and West Antarctica at a nearly 90-degree angle to that, and they are the black arrows. And that's the one that's really dominant within South Zealandia. And again, Andy and his colleagues and others have mapped where the evidence for this extension and where structures that can be put back to this extensional event can be seen across the continent. And one of the really strong features that they see are these transform faults with this orientation, today's orientation at about west of north. Following the extension, it was region of tectonic quiescence deposition, and then initiation of the Pacific plate boundary. So when all of this was happening, let's zoom in and look at what evidence we have for what was happening in the Marlborough region, in the region that we're looking at. So this figure is from retro deformation that James Crampton and others did, where they tried to restore the geometry of the blocks that we see today into a time frame around the time of breakup, and we've kind of put it together just into one figure. So these arrows of the two extensional episodes are from that previous slide, so these are averaged across the whole continent. And the reconstructions are based on restoring the displacement between major faults and distributed deformation between them, and also a vertical rotating it back, because one of the reasons Marlborough is quite complicated is there's been quite large vertical rotation since this time. But the main things I want to point out here is that these major faults, the Marlborough Fault, so the Hope, the Clarence, the Awatere, Hikurangi, are approximately perpendicular to the S1 direction and approximately within error parallel to this S2 extension direction. And we find evidence of both of normal faults, low angle normal faults preserved at various places within the Marlborough region that correspond to both extensional directions. There's also evidence from places where you can find that the sediments of that age caught within the faults. So, and there's also sedimentary evidence. Oh, the basin, the herring formation here for a large scale basin formed during S2. So we argue that these, particularly the eastern end of the major Marlborough faults, which is where we have sediments, still have sediments, and also some igneous rocks that we can use, that we argue that they were significant features in the Cretaceous. In some places, there's evidence that they're formed as normal faults during that first extensional, and then that they were active as transfer faults during S2. And transfer faults is those are like deep-seated faults. So once you've got a transfer fault through the crust, you've really got a long-lived weakness in that orientation, and we argue that that's been continuously used by the deformation as the tectonic regime changes. So following all of that, yes, we had a region of tectonic quiescence, sediments deposited. This is a sedimentary sequence in the Clarence Valley. Because of the uplift, a lot of this has been exhumed and eroded, but some of them are still there preserved, which are very helpful for our when we're trying to look back and look at the tectonic history and what's happened. So Alison Duval and her students have done a lot of great thermochronology across this region, including transects across the active faults here, so across the Hope, across the Jordan Thrust, the Clarence, and also Awatere, but that's not published on this map. And I don't have any time to do it justice here, but it's a really quick summary of what their results show is that the old zircon footwall ages show that the topography was built early, so that these thrust faults were active in the early Miocene. And then so with the inland Kaikolda ranges coming up first, and then the seaward Kaikolda ranges, and then from about 5 million years, it's really a pattern of just regional uplift. The whole Marlborough region is uplifting both the footwall and the hanging walls, and that fits in, of course, with the tectonics in that last region being much more strike slip than the earlier convergence. So reconstruction of this region is really complex. It's complex because it's right on that boundary. It's right. It's evolved a lot over the last 10 million years. It's evolved. It's moved. It's rotated. A lot of material has been exhumed and eroded, and there's been this complex block rotations. Francesca Giacetti used the model, G-Plates model, and she went back to 10 million years, and she took that model and then retro-deformed the units that we have to look at the evolution of this region. And she is largely focusing on the horizontal or strike slip movement. And if we go back to 10 million years, and this is her model. There's other models, but I found her model actually fitted in really nicely with the stuff that we were thinking about and what we were ending up, our sort of ideas. So by 10 million years, the Alpine Fault is as well established as the plate boundary. There's subduction happening off the North Island. Oh, you can't really see it on this slide. And then she was really focusing on what's happening between these two. And at that point, there's a lot of the relative motion to the north of the Alpine Fault is being taken up in northwest Nelson up and towards Taranaki on these north striking faults. Some of these are old terrain boundaries, and also what we now know as the Marlborough faults appear to be active right in the east, but she doesn't see any evidence for them being linked up at this time. The Kaweka terrain is a really useful marker, and back at about 10 million years, it was, if you reconstruct everything, then there's not much offset on any of those faults at that time. As we go through to 5 and then 2 million years, at 5 million year, a lot of the relative motion has been taken up on this eastern Wairau fault. Some people would link that right through to the Alpine Fault. Francesca has a western Wairau fault and a transfer zone between the two. And the Awatiri, the Clarence, the younger ones are starting to play a role, but they're not. But it's really mostly on here. And as we go from 5 million through 2 into present day, the strike slip materials, strike slip deformation starts to be taken up on the Awatiri, then the Clarence, and now it's the Hope. So we see in her model, and I think in some of the landscape, we see this evolution from northwest to southeast, but also from northeast to southwest. So here's our fault map now, and as I said, the relative motion has moved over the last 10 to 7 million years from mostly being taken up in this region and to the northwest through the Awatiri, Clarence, and now a lot of it's been taken up on the Hope. And when we make a map like this, we see these major faults, basically from Cook Strait going right, linking to the Alpine Fault. But when we look at the landscape, we don't necessarily see, it doesn't necessarily tell us the same story. So this is just Google Earth 3 times exaggerated. And here, there's the Wairau Valley, the Awatiri, Clarence, and the Hope. And in this region in the northwest, we see that those linear ranges, those linear valleys where we know the faults. But as we move to the southwest, we can track the faults. We kind of know they're there, but we're in much more of a blocky topography. There's this north-south as well as this easterly. You know, I don't think we could plot just by looking at this landscape that these really dominant faults are going through. Now we can quantify that. So Sam Roy has quantified this using a measure that he calls a measure of topographic anisotropy, which he calls EVA, every direction variogram analysis, which basically tracks the spatial persistent across an elevation, across the landscape of an elevation. So if this is a valley in this direction, that elevation persists, right? But in this direction, it only persists this far. And we can do that at a variety of scales. And so he has done that for Marlborough. So here we have, it's done at a scale of 1 kilometre. So he's just looking for the persistence of an elevation along in every direction at a scale of a kilometre. And here we see in the west, it's really dominated by this a north-south fabric and an east or east-northeast fabric. In the east, there's a hint of the northwest fabric, but we're not really seeing it because we're looking at too small a scale. If we move to the 5 and 10 kilometre scales, I mean, it really stands out. The strong northeast, these dominated by these valleys and ridges. But in this area, what we're seeing is, a northeast fabric which is cutting across a north-south fabric. So the fabric here of the Marlborough Fault is cutting across a north-south fabric. And that's why we're ending up with these blocky ranges. I need to speed up. And Alison Duval, in a similar thing, analysed the rivers and the faults. And she analysed the orientations of major rivers and compared them to active and inactive faults in the central or western region and eastern. And in the eastern, they all line up. Largely the inactive and active faults have the same orientation, basically northeast, and the rivers largely follow that orientation too. These are the rivers largely that need to turn around to get to exit to the ocean. In the central, we see a different pattern. We see that the active faults are similar orientation to down here. So the active faults are that northeast, are that Marlborough orientation, but the inactive faults are more northeast, and the rivers really sit within those faults. So to me, this is saying that there's this oldest fabric that the rivers are using, and that the new fabric, the Marlborough faults coming through, isn't dominant yet. There's lots of evidence for river capture. There's lots of 90-degree bends. So there's those new faults, which of course are weak. That area is weak, easily erodable. The rivers are starting to use them, but it's still dominated by that northerly. And I think there's two possible explanations for, or origins for, this northerly trend. One is that it's a Southern Alps fabric, and prior to the Marlborough faults cutting through here, this region was part of the early Southern Alps. So you'd expect to see these north-south structures, which we see. So this is a topographic analysis of the central Southern Alps, and this north-south fabric is really strong, particularly in this part of the region. And so it's reasonable to expect that might have been the case up here. But also it could be related to this signature, this faulting that was occurring off Taranaki and in northwest Nelson, again, before this Marlborough system cut through. But in either case, we have this earlier fabric, and it's been cutting across by this younger fabric, except that we've shown that this younger fabric has much older origin in the Cretaceous. So I think I'm doing well for time. So I just want to sort of pull it together and ask a bit of, where does the Marlborough system go from here? So, I hope I've shown that we've got an evolution northwest to northeast, so from the Waiara to Awatere. So, and with most of the relative plate motion now being taken up on the Hope, which is coming through here. We've also, at the same time, had an evolution from northeast to southwest. So these are really well established. As soon as the tectonics needed a strike slip fault in this region, they were there to be reoriented. But as the deformations moved to the southeast, it's had to kind of realign. It's had to cut across those north-south fabrics that pre-existed. So will this deformation just continue out and another fault propagate here? And sometimes we talk about the Portus-Vas Ambly as a possible new Marlborough fault, but actually I now argue that it's not going to continue, and it's not going to continue because of this this feature here. So this is the Kaikolda Peninsula right beside the Hope. This is the Kaikolda Peninsula here. And so it's right at this boundary where the Chatham Rise. And what the Chatham Rise is Cretaceous subduction. So this is, I'm going to skip the slide because I've got it here and I'm running out of time. So this is the picture today. And the color coding is relative motion. So Australian plate moving as Australia, pink moving as Pacific. A lot of this material is now moving as Australia. And if we go back in time, we see that where the deformation or the locus of deformation was much closer to Australian boundary. And that means it was a lot further away from this Chatham Rise. But now we're impinging against the Chatham Rise. And I think what's going to happen, or what I think is going to happen, is nicely illustrated by these two cross sections of Donna Eberhard Phillips. And these cross sections, so there's one across here, across the Marlborough Faults, and across the area, so near Kaikolda, which would be similar to what we saw in the past. And then there's one across closer to Christchurch and across that boundary. Now this is P wave attenuation, but really what I want you to kind of look at is if it's low, where we've got warm colors, that's basins, active faults, and the brittle crust. So up here, it means that there's distributed microfractures, or in the ductile truss, we've likely got localized ductile deformation. If it's high or cold, we're seeing the slab or mafic or strong mafic rocks. So the difference between these two, between these sections, there's a couple of significant differences. One is that instead of just deepening like the slab is shallowing off, and so there's not that deepening of slab with the potential for deformation over here. But more importantly is that here, so under our current active faults, we have the slab is at about, or the strong material is at about 25-30. So we've got a thickness of ductile crust. We've got a thickness of ductile crust that can deform. By the time we get down to this section, we've got the strong mafic crust at about 12 kilometers. There's really no ductile crust here. So what we're going to end up, and this is an old image of Phil Barnes that I think it shows it really nicely. At B, where we've got that thickness of ductile crust, the ductile crust, it can deform, and the deformation on these strike slip faults can deform, it can flow out over the oceanic crust here. But once we get down here, it can't expand. It's going to hit the Chatham Rise. It's going to hit this really strong material. So it's going to act like an indenter. And so I think, I think Peter Coons is on the call, and he's known this for many years. You know, the nature of the lithosphere and the structure means that I think we're going to end up with a boundary that's kind of stuck here. It can't expand, continue to expand out to the southeast. So this is the summary. I'm just going to leave it there to read. Actually, I'm going to go to the next slide because that's got my acknowledgements. But I hope I haven't taken too much time. Dina.
Great, thanks, Phaedra. Very interesting talk as usual from you. I don't see any questions yet. So I suppose I'll just ask my question first.
Sure.
Can you explain again why, like, what you meant by how it's more like it has more of a north-south or like blocky fabric kind of in the central? So are you saying that's because the Marlborough Fault System hasn't almost reached that area yet, so the topography is not responding? Or you thought it was because you have this other system like the Taranaki system that is influencing that more?
I think that there's no doubt the Marlborough Fault System has reached that, because we see those strike slip deformations. Geodetically, it's all strike slip, but the landscape, there's a lag. So the landscape hasn't had time to catch up. And so you've got these older north-south structures, which lots of them are mapped. Lots of those valleys aren't mapped as faults, but I'm convinced they're faults. Lots of them are mapped as faults, but they're inactive. But they're still, but to the rivers, they're still weak faults. And so the rivers the rivers are entrenched in those structures. And so it takes quite a while for the new faults as they come through and they weaken. But and there's river capture happening, and a lot of the rivers have these, 90 or greater degree bends, and that's where they've been captured. But it hasn't happened enough so that there's one river or a couple of big rivers running along the Marlborough faults there. They're just fragments, and so that's why you're ending up with these blocky ranges, because they're bounded by both fault sets.
Right, cool, makes sense. Okay, Any other questions? Feel free to raise your hand, or the chat, I believe, is open if you want to type it.
I will just ask, what was the lithology in the region? I just saw the names, but I couldn't catch what lithology.
Oh, sorry. It's so it's Greywacke. It was formed in the on the crationary prism. So it's
Okay.
low grade Greywacke.
Okay, cool. Thank you.
So, I mean, I'll ask a very a naive question, I guess, if nobody else has any questions. So if you expect kind of the tectonic movement to slow or kind of get stuck, do you think it will impact uplift rates in this area?
Yeah, that's a good question. I guess yeah, I guess I think you will end up with an oblique, which we've got now, oblique collisional zone. And at the moment, it's really dominated by the western side and the huge erosional, so all the exhumations over on the west side. But as it gets jammed, as it has an indenter to the east, which it hasn't really had before, I'd expect, I'm just making this up right now, I'd expect sort of a fold and thrust belt to end up growing over that region. And if it can't deform the rocks of the indenter, then it is going to have to increase the uplift rates.
Okay, great, super interesting.
Yeah.
So if anybody wants to, again, or maybe I'll just mention it again, you can use the reaction tab at the bottom of your screen, and then there's a kind of hand face signal, and we can unmute you. So if anybody has any more questions, feel free to do that. And if not, then feel free to use the chat, or we'll wait a few more minutes for people to come in before we start Anthony's talk.
I'm sorry for all the geodynamics. And feel free to get in touch if you want to just, if you want to.